Hi, if you stumbled upon this video, you are probably in the same boat that I was once in, trying to cram in information for my organic chemistry exam. With my organic chemistry workbook here, a snack, a lamp, calculator, pencil case, some markers, highlighter, and scrap paper. But if you've been paying attention in class, you already know your class notes. You already know the concepts. So let's go over them. Let's review them. Stereochemistry. Stereochemistry is a part of organic chemistry that focuses on three-dimensional arrangement of atoms and molecules. In order to dive into organic chemistry, you need to know what stereochemistry is and the relationships within stereochemistry. Symmetry and chirality. Asymmetric objects are chiral and symmetric objects are achiral. Let's look at the left. Cis 1,2-dimethyl cyclohexane is achiral. Trans 1,2-dimethyl cyclohexane is chiral. So, chiral conformations given here are now in equilibrium. The molecule is achiral. Let's take a look at chiral centers. So you have to make sure that you have chiral centers in the molecule. And having a three-dimensional formula given doesn't necessarily mean that there's chiral centers. So when looking for chirality centers, you have to assign priorities to the atoms attached to that center. And the highest priority will go to the atom with the highest atomic number. So in the case that there are isotopes, you would use a mass number instead. But if two or more of the atoms are directly attached to the chiral center of the same type, you would look at the next atom so you could break the tie. However, you can't do this unless there's a tie present, so you repeat this process until the tie is broken. So if there are atoms containing double or triple bonds, you would count them twice or 3 times. Now, this holds for each of the atoms that are involved in the bonding. You can see how this becomes this. You can clearly see this. Now, let's take a look here. Cyclic molecules and chiral centers. So here there's no chiral centers present. Here a chiral center is present with the R configuration. Let's talk about the Fisher formula. So Fisher formulas are easily translated into bow tie formulas, which are known as 3D formulas. The order of the priorities would follow a clockwise direction in the Fisher formula. Fisher formula, 2D representation of a three-dimensional organic molecule by projection. So since it follows a clockwise direction in the formula, the actual configuration of the molecule would be S. The order of priorities follows a clockwise direction in the formula. So now that we've went over configuration, let's take a look at configuration of R and S specifically. Now, the diagram below shows possible combinations of configurations for molecules with 2 chiral centers. Since each chiral center can be R or S, the combinations that are possible are SS, RS, SR, and RR. If the 2 molecules are mirror images, their configurations are exactly opposite and they're enantiomers. But if they're not mirror images, but they're still stereoisomers, then they're diastereomers. Now, let's go to the last part. Orgo is not easy, but one thing I learned in Orgo is that breaking down the steps and making sure you understand each concept can go a long way.